So before we jump in, I want to answer a question, or partially answer a question we asked yesterday. So remember, we had this condition that the sound speed is less or equal than 1, which means less or equal than the speed of light, which is physical, but Martin asked, okay, but at least mathematically, if you assume that the sound speed is greater than 1, does something go wrong? So I thought a little bit about it, and so here's a partial answer. So if you write your Euler system as a first order symmetric hyperbolic for the variables the enthalpy, the velocity, and the entropy, right? So what you need that this guy is 0 to apply the standard energy estimates for first order symmetric hyperbolic system. You needed this guy's positive definite. Particular cell has to be invertible, right? But now if you compute the determinant of 0 and everything here is relative to standard Cartesian coordinates, you're going to get something that's 1 plus ui to the 4, 1 plus 1 minus cs squared uj. This is positive because here is only the spatial components. I'm doing this for the involved schematic. But look at this term here, right? So if c is greater than 1, this could be negative. This would be negative, right? And then depending on the value of the velocity, the determinant could be 0. So this matrix will not be invertible. So you could not apply the standard formalism to get the existence and local existence units. Now there's an alternative approach that I kind of sketched yesterday due to Likinerovich. But for that, you also need this matrix to be invertible because remember, in the Likinerovich approach, you couple to the vorticity, so you need to derive initial data for the vorticity. For that, you need to solve for the time derivative of u. So this is not saying that you cannot do the problem if the sound speed is greater than 1, right? Because maybe there's another approach, but the two approaches that are standard, that are textbook material, don't work. And because it's not physical, then I don't think it's worth spending too much time thinking about whether you can do it or not. That's just a partial answer to what Martin. So is this okay, Martin? Thanks for your question.
Yeah, it's great. Thank you.
Okay, so I want to go back to where we were yesterday. So remember, we were trying to do this bootstrap argument. So we start with our bootstrap assumptions to close the L1 in time and infinite in space norms of derivatives of the fluid, the wave variables, right, and the vorticity. So from here we get energy estimates. And then I briefly told you yesterday how we do Holder estimates, but for transport equations. So there's this argument that you have to control the regularity of the flow lines of it. So this is like we discussed yesterday. And then the logic goes that from the energy estimates you get controlled from the acoustic geometry, which leads to boundaries of the conformal energy, decay for linear waves in the background, linear streaker estimates, and finally improvement for the wave part. Now, these three steps here are the ones that you are really relying on techniques from general relativity and nonlinear waves. So this is almost like you want to just quote the results. You cannot simply quote them because you have to verify that all the reductions that are carried out are consistent with the transport variables that you have in your system now. Okay, but this is the part that say that's like the least new part in the argument. Now, of course, the control of the acoustic geometry is also relying on techniques from GR. In fact, it's at the core of things like going back to stability of Minkowski space. But I'm separating this because here you also have to do some hard work because here's where you're going to see the interaction between the wave and transport components, and you're going to see that in particular because the transport variables appear as source terms for the estimate of the acoustic geometry. I'm going to discuss this briefly. Okay, so that's why I'm separating this part from the rest. But once you have that, then once from these two arguments you can improve the bootstrap assumption for the transport part. One last thing you have to be careful here is because in this entire argument, at some point, since you have these transport variables appearing here, one thing you do in the control of the acoustic geometry, you have to do estimates along cones and estimates along the spheres. So in particular, you have to do some holder estimates along the spheres. So in the end, you're going to have to get some holder control for your wave variables. And you have to show that the Holder control for the wave values that you get from here is consistent with the Holder control from the transport value that you get from the step here. Okay, so everything has to fit together at a consistent regularity level. But that's so that's what we're going to do today. Okay, now to discuss this, I'm going to discuss most of these steps. We'll discuss them in a more or less reverse order. Okay, why? Because, well, that's how the argument is structured once you have the proof, but when we are trying to prove something, that's not how we think, right? You start with what you want to prove, and okay, to prove this, I need this, then you realize you need this, right? And that's how you think when you're trying to prove something. So I'm going to discuss them in more or less reverse order. Yeah. Okay, so then there are several reductions, okay? And basically, to get the control that you want, again, remember, you want to control this guy. I mean, you want to control L1, but remember, the answer suffices to control L2. There are several reductions that tells it suffices to get a frequency localized. Striker's estimate of the following form. So we have the Euler projection of the phi, and this is going to be some LQ in time, L infinity space. You want to control this by lambda to the 3 over 2 minus 1 over q d phi L2 of the initial wave. Okay. And here q is some number is slightly greater. Okay. So you want to get an Striker estimate. So there are a series of reductions that come in this part here, which involves some rescaling of the variables. So these reductions involve some rescaling. And what is phi here? Phi is a solution to the linear wave equation of phi equal to 0, but is a linear wave equation on G background, the acoustical method, right? And how you get to some for the linear wave equation, because in these reductions, in the end, there is some Duhamel argument. There's some Duhamel argument that kind of reduces things to a linear wave equation. Okay, so that's part of the argument. So this is a technical thing, right? So several reductions, rescalings, but even though it's technical, follows very closely what has been done for nonlinear wave equations. So all we have to check is that the reductions are consistent with these additional extra variables that we have now. Okay, so this is not a big deal. And then there are further reductions you can do. Now we have this frequency localized guy. In fact, suffices to localize at frequency 1. Okay, so it suffices to, you can further reduce the problem to a Striker's estimate of the form P phi LQT and infinity next, and this is when they controlled again by d phi L2 of data. And here P is the Euler projection to unit frequency. So let's say we take 1/2 C S2. So once you localize in frequencies, right, you can imagine, you can rescale all the localized frequencies to a frequency 1, and you reduce to an estimate of this time. So again, this is another type of reduction that goes back to constructions, and what you have to do, you have to follow the things that people work really hard before to accomplish, and just verify that everything is consistent with these extra values. And then finally, there's a further reduction where you can prove that this estimate follows from a dispersive estimate. Okay, so then maybe I can erase this part here. Do I still need this? I think I don't. Okay, so this frequency localized follows from the following dispersive estimate. Okay, so let me say the dispersive estimate, make a few comments. L2 sigma t. So this is going to be controlled by something that's going to be 1 over 1 plus t 2 to q of t times d phi L2 sigma 0 phi and again, this is for solutions of the linear wave equation. And let me explain what these guys are. First of all, so just to give an idea of how you reduce these for dispersive estimate, right? Because they look, and I briefly mentioned this yesterday. So this comes from a sort of function analytic abstract argument called T star. So this is a type of duality. Okay? So this is a duality argument. And again, it's another technical thing, but if you haven't seen this, just roughly you can think like this. You want to control some mixed space-time norms. So you're going to use a duality which involves a mixed space-time norm. And in the end, you have, because you're integrating in time, you need to get some type of integrability in time. And that's what decay is basically telling us. Things are going to be kind of integral in time, right? Because they have the right 1 over t power to get integrability in time, okay? But we really have to go back and see the full abstract arguments to understand how this is going. Now, so that's the first thing. But one important thing to observe here is that you see, we went from having one full derivative of phi to having the b derivative. Remember, this is the material derivative, right? This is the derivative, the direction of the velocity for materials, right, in space-time. And the reason is because, again, you have to control all the derivatives, but when you do the T star argument, spatial derivatives essentially can control by integration by parts. Okay? The spatial derivatives you can always integrate by parts. So when you do the abstract argument, the spatial derivatives you can control integrated by parts, and you're left with something that's like a time derivative. Except it's not fully time derivative in the sense of the Cartesian time variable. When you do this argument, this duality is geometric. So that involves a current, involves some type of energy current, it's a geometric in nature. And because you're doing something geometric, the correct time direction has to be the orthogonal to the constant time slice. Look at the constant time slice sigma t, has to be the orthogonal, but of course it has to be the orthogonal in the acoustical metric. And dt is not orthogonal. Okay? But d is. Okay, so the acoustical metric is orthogonal. One thing that I didn't tell you, but you can quickly verify, is that this guy is -1. It's normal, like the acoustical metric. Okay, so because of the geometry that comes in the argument, you get rid of the spatial derivatives by different parts, and the quote-unquote time component that remains is really a geometric time component, which is the b derivative. Okay, so that's why you can trade a full derivative there by a b derivative. Okay. And applying a little bit here, this really is not at time 0. There's another reduction that you have to make where you really consider the problem at time t for 1. But again, there's a small technicality. You can really think it's time 0, okay? Okay, so that's what we have to do. And of course, I didn't tell you what this function d is, right? Now, this function d is such that d L Q over 2 in time is bounded. This function d has the same integrability in time as this factor. And the way you can think of this is that this is like coming from the linear wave equation. So if we're doing this for the linear wave equation, this will be what you get. So this factor here is quasi-linear in nature. So this factor here is really coming from the coefficients that you're getting when you're going to do your estimates. You're going to pick up derivatives of these coefficients that you have to control. So the quasi-linear nature of the problem, or rather the fact that you are propagating these linear waves into this rough background, is contained in this function. Okay, and to show that you can get this estimate, really boils down to show that, you know, when you do this estimate, you get, let's say, what comes from the linear wave plus something that you have to control, right? And that's what's coming from the coefficients. Yes.
The null condition play a role there.
Say it again.
Does the null condition play a role there? Relativity of dt.
In here?
The dt part.
No.
It's the nonlinear part, no?
Yeah. So okay. The nonlinear, the no forms, you mean?
Yeah.
Okay. So yes and no. One thing that I didn't tell you, but I will say before the end, that once you finish the argument, the fact that those Q's are no forms is not important. What is important is that they're quadratic. Okay. So the fact that the nonlinearities are no forms is not relevant, but it's crucial they're quadratic. And you can see that because when you're going to estimate quadratic things, you're going to do L2 L infinity estimates. Now, if this is quadratic, you're going to get something L2, something L infinity, and the L infinity time is the L infinity guy, when you integrate in time, it gives it the mixed space-time norm. But suppose you had something L infinity that, I don't know, it's quadratic. Suppose you had something that was cubic, then you do L2 L infinity, you're going to get something L infinity. And then you integrate, you no longer have the mixed space-time norm. Then you cannot do Strickland's estimates, as far as I know. But so everything will break down. So it's crucial it's quadratic. It's not important there are no forms. Does that answer your question? Okay. Okay, so that's it. And then there's one last reduction that you can do, it's the following. Because everything now is at fixed frequency, you can just use Bernstein's inequality to replace this L infinity by L2. Okay? And then L2, you know, we like L2, right? So we can do L2. Right? The whole point now is how to prove this decay estimate. So let's talk about decay properties of the acoustic joint. Then the first observation, which is probably known to everyone in the audience, right, is that if we look at an equation like that, the decay properties of solutions to an equation of this form are directional dependent, right? So the whole point is that derivatives that are tangent to the characteristics decay better than derivatives transverse to the characteristics, right? So let's see. So maybe I can draw a picture here. Yes. So you have let's say this is a flow line of B. Flow line. Then here now I can let's say draw sound cone. Actually, the sound cone. And then the whole point is that derivatives that are tangent to the sound cone, so these are, let's say, tangent derivatives, the tangent, or like this, right? They decay better than derivatives that are transverse. Okay, so this is like a transversal guy. So this guy is good. This guy is bad. And of course, that's something that's already true for the linear wave, right? Just using the representation form, you can already see for the linear wave. If you haven't seen this, you can just look at the linear wave equation, and the statement is that it's a lot of hard work for no linear waves you can prove similar things. Transverse, tangential to the cones, this is a decay better than tangential to the cones decay better than transverse to the cones. Okay. Now, so what we need here now, we need to get a. So we talked about the cones in abstract, right? But now you really need to kind of get a hold of the cones, right? So you need to really kind of write formulas to characterize. And again, this comes from GR. When you do that by introducing an iconal function, right? If you introduce an iconal function, the solution to this fully nonlinear transport equation, right? With suitable initial conditions. Okay, so there's a part in the paper where we have to discuss how to construct initial conditions. Again, because at a lower gravity setting, you have to think about this stuff. But that can be done. And then, of course, the level sets equal to constant are the sound waves. So that's what we're going to do. We're going to introduce an iconal. And then this, let me make a parenthesis here. So something we were talking yesterday. Again, these are ideas that probably are known to the audience because they come from relativity and they goes to the heart of the philosophy of relativity to work with iconal functions and so on. But then here you can understand why the Einstein-Euler problem is very difficult. Because for doing Einstein equations, you pick an iconal function, right, using the space-time action. Now, if you're doing Euler, you pick an iconal function using the acoustical action. And of course, they don't agree. But which one you pick, right? Because your arguments are always tailored to one iconal function, right? And now, if you have two different ones, then we don't know how to run this type of arguments, or many of the arguments that we have. Okay? So that's just a parenthesis telling why Einstein-Euler is hard. Okay, so then you do again the usual thing. We construct a null frame, a null with respect to the acoustical metric, right? So you look at, so these are the sigma keys. You look at these spheres, the intersection of the sound cones with the stigmatic constants. And then on the spheres, you can look at the normal, right? And then you also have the vector field B, right? Remember, B is the guy that really is like DDT when you do like for the wave equation, but here it's like the correct time-like vector here. And then you construct a vector L, which is B plus N, and a vector L bar, which is B minus N. And then you complement that with two orthonormal vectors of the sphere, and that gives a null frame, right? That gives a null frame. So basically, you are doing. So you can really see how these techniques are coming from GR, right? So I guess it's an interesting point that I didn't emphasize yesterday. How maybe 30 years ago, if somebody told you, we are going to solve problems in fluids using ideas of general relativity, that would doesn't seem to make much sense, but that's what we are doing now, right? Which of course speaks to the powers techniques, right? How they trickle to other fields. Okay, so the whole point in the end is to get, remember, to get a decay estimate for this guy. So so to get a decay estimate, what we do, you have to use some. In the end, you have to consider some weighted energy. And to do that, we need to basically use weighted multipliers. So you're going to multiply your wave equation by some suitably chosen vector fields apply to phi. It is vector and some integration by parts, right? And then there are going to be two types of vector fields we're going to use here. The two vector fields we're going to use are going to be some suitably chosen function of R tilde. So R tilde here, right? Let's see, yeah. So R tilde is t minus u, so use the Arconal function, right? So, so again, if you haven't seen this, just think that this is the analog of the standard radial variable in Euclidean space, but now it's the analog where everything is tailored to this geometry, right? The acoustic geometry. And these are going to be going to give the kind of weights that you have, like again, like for the linear wave equation, you can use R weights. And then you're going to use two multipliers, right? So this one is a multiplier that's good in some interior region. So if you're in some interior region, some region here, this multiplier is good. But what happens is that I'm not going to tell you this function R has to be, but this becomes very weak when you go far away to infinity. So this gives a good estimate in some interior region. And here is the opposite, right? So you're going to use a multiplier using the vector field L, which becomes weak when R is kind of near zero, right? So this is going to work in the exterior. So we're going to have two different multipliers, one for an interior region and for an exterior region. And I'm lying a little bit because, for example, this guy here had to add something as a low order term. Let's not worry about that. But the point is, if you do that, you see this guy here, in the end, is like doing a Moravec estimate. Okay? It's like a Moravec estimate. And again, if you're doing the linear wave, this is exactly dr, and this is a function of r, and that's how you get the Moravec estimate, which in the end gives some integrated energy. And this guy here is like the RP method of the Formos and Wozniacki. Okay, so those are the vector fields we're going to use. So let's see, I think I can erase this part. What we're going to do, we're going to multiply wave equation by those vector fields, right? By f r tilde n phi or r tilde n l phi, and do what you're always doing with these integrated parts, right? Integrated by parts. Okay. Okay, and then here is how you we're going to get into the geometry part. Because when you integrate by parts, you want to take derivatives of L and derivatives of N, right? But you see, these vector fields L and N, they're constructed out of the geometry, because they're constructed out of the sound cones. So ultimately, they depend on the regularity of U, but the regularity of U depends on the regularity of your metric, right? So this is a full nonlinear, a transport equation, and so don't expect U to be any better than the regularity coefficients, right? So, if you unwrap, I'm not going to do this, but if you unwrap all this all the way back to what this means in terms of the regularity of the original variables, you're going to see that just by counting derivatives, these guys are not regular enough to close the argument. So that's the whole point. So you need to, at least as written, they're not regular enough. So you have to show that they have better regularity properties than the naive derivative count. The naive derivative count tells that they're not good enough, so I have to show that they actually have better regularity properties. And the way this is done, again, this is going back to GR. The way that this is done is that you can decompose these guys into this null frame. Now, if you have a vector and you decompose a null frame, those are connection coefficients, right? So those are the connection coefficients of the null frame. So in the end, you have to control these connection coefficients. Now, the connection coefficients, the whole point is that they are geometric objects. They are like, the second fundamental form, the null second fundamental form, the trace of the second fundamental form, and so on. They're all objects that have geometric meaning. So that's why this idea of geometry comes in, right? So everything boils down now to control these connection coefficients at the regularity level that we need to close our estimates in this low regularity space. And again, I know that everything that I said probably is known to the audience because this comes from GR, but I think it doesn't hurt to just mention these again. Okay. So then, control of the connection coefficients is done by using a very delicate evolution system, which are the known structure equations. Okay? So there's a bunch of equations. It's a combination of evolution equations and elliptic equations that are satisfied by these connection coefficients. And those are the equations that we're going to use to derive estimates. Okay? Now, the system is like a very long system. I'm going to write down. Let me just point out one of them. Okay. So let me write a punchline here again. I mentioned this yesterday, but let me write down. So you can, to close the argument, we need okay, so we can only close the PD argument, right? If we have close the PD argument, if we have a complementary control of geometric objects. Okay. Now, if it were possible, if one day somebody discovers a way of controlling this guy just as integration by parts, so like that, then this whole machinery of the geometry we could ignore. Okay, so this whole business with the geometry we would ignore if you could just go back and do like some standard PD purely technique to control these derivatives. But as far as we know, that can't be done, right? Okay, now one connection coefficient that appear. I'm not going to discuss all of them. I'm going to discuss only one of them because this is one of the most important ones, one of the most delicate to control, is the null curvature or the null expansion, right? Which is like trace G bar chi G D E A L E A. So take a trace here, so I'm standing over E1 and E2, and G bar. So G bar, sorry, G slash, not G bar. Slash is the metric used on these spheres, right? So you look at these spheres, right? Then the acoustical metric uses a metric there, and that's the. So that's all the quadratic coefficients that you have to control. That's it. Oh, okay, so this is like the sorry, the GT. Oh, sorry. Okay. In this guy didn't tell. So this is the covariant derivative with respect to the acoustical metric, right? Okay. Now to control this guy, you have to see which equation satisfies, and satisfies the Reichardt-Euler equation, right? I don't remember how to write Reichardt-Euler. Right? It's a transport equation for potential, which has the following form. Okay. So these are the two null components of the rich curvature, right? And again, the rich curvature of the acoustical metric. Okay.
Does that have a sign?
Huh?
Does that have a sign?
What do you mean?
Reichardt-Euler's got, has monotonicity in GR. So
Yeah, so there's a lot of them on trace G here that has a good sign, but that's not them worried about. We're worried about this one.
yeah, and is this time?
No, but it has a good structure. Which I'm going to tell you now. Okay, so so this guy here. Okay, let me erase here.
I just asked because in GR it has a sign, right? So
Yeah, but so okay, so of course, if you're in vacuum, right, or if we have some energy conditions, right, but we don't have any of those two things. That's what you're referring to?
yeah.
Yeah. So yeah, but we don't have those conditions there, right? Does that answer your question?
Yeah, no, it does. But are there natural conditions you could put? I mean, Reichardt-Euler's right.
Right. Okay, so okay, so let me translate your question. So the question: are there conditions on the fluid that you can impose that this guy has a sign? I don't know, but that's an interesting question.
Because the point is that the monotonicity in the GR case is like crucial for many things, right?
Right.
For all kinds of things, right?
And you don't have that here because you don't have a sign.
Yeah.
But maybe the question is like, are there interesting class of fluids for which the guy has a sign?
Exactly.
I have no idea. It's an interesting question. Okay. Now, what we do here, there is a special decomposition of this guy that goes back to the work of Jansky on the improved local acoustics for positive wave equations. So, using a special decomposition of Ricci, you can rewrite the equation as follows: L plus gamma L equal Einstein to take, don't remember, those are mine. Alpha and beta, G U, G alpha beta. Where here, this guy is L alpha gamma alpha, where this guy is a contracted Christopher. The whole point is that this gamma L goes like one derivative of G, which in terms of our values is like one derivative of psi. Okay, that's the. Okay, then I'm going to tell you why I'm moving this guy to the left side. Okay, so we have that. Now let's use this guy for decomposition. So why I'm moving this guy to the left? Okay, so you in principle could keep this guy to the right as a source term. Okay, but you can't. Okay, so this guy cannot be a source. And the reason is therefore, let's do derivative count. Okay, so if you move this guy to the right, then you're going to get this object that that's going to involve basically two derivatives of psi. Okay, but let's see.
Something like that.
Huh?
A lacting is gamma. So the gauge term for the DR, right?
Yeah.
That term.
Yeah.
You don't have that, and if you don't deal with that yet, right? You can't do anything with the contact, right?
Okay, so in a certain sense, the kind of freedom that you had, you already used the decomposition of the reach, okay? Because that's especially the composition you're using, right? So that's right in a certain form, right? So from here you can okay. So one thing that we have to do, we have to derive estimates along spheres. Okay. Now, so if we want to derive estimates along spheres, so we want to have to look at the restriction of these guys along spheres. Okay. But there are several norms you have to derive in spheres, but one crucial is that you're going to get a sort of L2. In fact, some exponent is slightly greater than 2, some LP with is slightly greater than 2 on the sphere. Then we're going to take an L infinity norm on the U variable and L infinity norm on the time variable. So point-wise, this guy on the sphere then has to be something controlled. Now, the problem is that in the end, you have to derive not only estimates for the trace, sorry, so the trace of chi, but you have to derive, you have to take one derivative of this equation. Yeah. Okay, so you have to derive estimates for the derivative of this guy. Okay, and then if you differentiate this guy once more, you clearly see that you don't have enough derivatives. Okay, so that's why this guy doesn't have to be a source term. So the goal here is to move to the right and eventually try to control this combination together. Okay, so that's why in the position of reach, you move this guy to the left. Now, this part here, so this is essentially telling you that here you have what? You have box G of G, right? But box G of G, remember G is like G depends on psi. So after you do the chain rule, this is box psi. And now we have the equation satisfied by psi, which is code of, remember, And then that variable C, right, which is the vorticity of the vorticity, which I'm kind of just think as something more complicated, some combination of variables, but as I said yesterday, I'm cheating a little bit. I think that the code of vorticity. Okay. So the whole point now is that you need to have this source term at a regularity level that's consistent with the estimates you're going to control, you're going to derive for this object, right? And as I said, clearly here you're clearly seeing the interaction of the transport part with the acoustic geometry. So here is acoustic geometry, and you have a source term that is transport part. This guy is not there if the fluid is in rotation. Okay. Okay. That's what you have to do. And then, of course, whether or not you can control this guy depends on the kind of estimates you need to derive. Okay. Now, one thing that you need when you're doing these estimates, you need to derive estimates along cones. Okay. So one thing that you need to control, you're going to have to control tangential derivatives on the right-hand side, sorry, on the left-hand side, in L2, but it's going to be L2 of the sound cone, right? This cone. Okay. So when you go through this argument, again, this goes back to how the estimates for the acoustic geometry are done, going back to GR, that it is to control those error terms dn and dl. It's very important how you integrate things. You cannot just do a kind of a space-time integral, right? You have to, in the end, your error terms have to, it matters to integrate, if you get your space-time integral as an integral first along cones, and then in the time direction and so on. So we have, all the decomposition is very delicate. And one thing that turns out you need to control this quantity, which means that you need to control this guy. So we're going to differentiate this equation once. You need to control one derivative of this guy on the cones. And now here we think the argument dies, because this satisfies a transport equation has no connection with the cones. There is no reason why a transport equation is going to allow you to derive estimates along cones, right? If you have a transport equation, you're going to be able to derive estimates along constant time slices. Okay. So here's one of the proofs of the matter. And what saves us are again the special structure of the equation. Okay. So what happens is the following. And let me just say that I'm cheating a little bit here. You do need this estimate, but in the end, you also need something slightly stronger. You need to derive something for a slightly bigger exponent. But let's stick to L2, which you also need at some point. And so what we have here then is the following. How you want to control this guy, right? So the question now is how to control one derivative, one derivative of the curve of omega, L2 of a cone. Okay. So let's define a current which is going to be the following. It's going to be of omega, and this is going to be a current, so the vector field times b. Okay. And then if you compute, right, to do this guy, this is going to be what? It's going to be v slash omega times b. So this is a computation you have to do, but okay, one derivative of this guy will involve this guy. Sorry, there's a square here. That's very important. Right, it's going to be this guy times the derivative itself, and if you reorganize things the right way, that's a big derivative. Okay. Okay. And then what we're going to do, we're going to do the following. We're going to find the divergence theorem. 0 to t, sigma t, but only the part interior to the cone. Okay, so if you apply the divergence theorem, the part interior to the cone, then you have that that term that we have there, equal omega d slash omega is going to be one interior to the cone, maybe interior to right interior to divergence. And then you do what you always do, integrate by parts, divergence, right? So if you integrate by parts, you're going to get a boundary term is the cone. Plus another boundary term on the upper part, okay? Plus data. And I'm lying a little bit of data because you're integrating this between two guys. But data is really here at the tip of the cone, right? So you integrate on a sigma t here, and another sigma here. So this is related to the fact that in the end you do some estimates not at zero, but at a different time. But I say this guy here is control. So you get what? So you're integrating in the interior, and you get a boundary term that's the cone, right? A boundary term that's here, and a boundary term that's here. That I'm roughly saying it's data. Okay. You can think it's data because they got on the lower part. Okay. Now,
Wait, can you explain that again? Like, why is that data?
I mean, it's not really data. You have to handle stuff, right?
Right.
But what I'm saying is that in the end, you have to choose these two slices correctly, and the treatment of them is kind of no equivalent. But if these slices were all the way back to time zero, it would be data, right? So I'm being sort of unprecise here, right? But the whole point is that whatever this is going to be something at the same level as this, and these guys here now. So this guy, if you take the G product of J and B, is exactly the term of sine deco d squared, and the integral on the slices of this guy are controlled by the energy estimates. Remember, if you start the argument with the bootstrap, the first thing you did at bootstrap was energy estimates. So this guy here is controlled by energy estimates. This guy is controlled by the energy estimates.
That's omega.
Huh?
Omega, not B.
Yeah, sorry. Okay. Now, this guy, you can use the equation. So the equation, remember the equation B co omega is like this side. So B d slash co omega is going to be like two derivatives of psi. And then if you do Cauchy-Schwarz, you take this guy squared, by energy estimates, both these terms are controlled on sigma t. And then you're just integrating in time. Okay, so here you need to do Cauchy-Schwarz plus energy estimates, and both guys are controlled. Okay. So what about this guy? Now, I didn't tell you this vector field V, right? But V is the vector that's normal. You do integration by parts, you pick a normal. But the normal to the null surface is also tangent, right? So this guy is a vector that's going to be null. Now, of course, as you know from GR, there is no Riemann metric induced on a null surface, right? So this integral here, everything has to be done. And you do the usual thing when you do the integration by parts, pick a boundary term that's null, right? You have to choose coordinates, and you tailor your choice of coordinates to something that gives a specific volume element, right? You can do that, but that's kind of a sort of gauge argument. But then the whole point is that if you do this the right way, so that if you pick this V correctly, which means you pick your coordinates correctly, then this product here is equal to -1 if B for suitable V. And that's happening because that's happening because J, sorry, okay, not -1. So G, the inner product of B and V is -1. Okay, for a suitable V, right? And that's happening because B is unitime line. So the picture should have in mind in box space, if you take this vector here, right? 1, 0, and the vector 1, 1, it's null, the inner product is -1. Right? So this is like our V, and this is like our V. Right? So this product is -1, but I have this term here, right? So this guy here gives precisely minus d slash rho b squared, which this minus cancel, and this is precisely the L2 norm along the cone, which you want to control. So these guys control, these guys control, these guys control, move everything to the other side, you get an estimate for the L2 norm along the cone. Okay? So the crucial thing here, the two crucial things are the following. This works first because this vector field B, since B is unitime-like, it's always transversal. The cones. If B were an arbitrary vector field that you're transporting, this could be anything, right? B could cut here at one point, here at one point. There's no way to, so this could be positive, negative, or zero. This is the problem, right? So it's crucial that B is transversal to the cones. That's the first key observation. The second key observation is that here we are using the equation. And remember, the equation for the curl of omega gain a derivative. Right? Because remember that b omega is like one derivative of psi. So if I take the curl, plot out the derivative, I'll get 3 derivatives of psi, one too many, right? But the point is that even though this equation is true, remember the equation for the curl, there's a cancellation. It also involves only one derivative. And that's why this works. I have to use the equation. Okay? In particular, if this were instead of a curl, an arbitrary derivative, so just an arbitrary coordinate derivative, then you couldn't use this equation. You'd have to use this one, and then you would lose the derivative. Okay? So here's like the structure of the equation really helpful. Okay? And remember, every time I write curl, I really mean C, the variable C, right? So in the end of this is really the variable C that appears here, but you know, I'm writing curl just because it's simple, right? But so this is how we get. So we have sort of this these two structures: the transversality of B and the equation satisfied by C or by the curl in our case, that really come together here to get as the only point. And then this is what lets you close the estimate for this variable, right, along cones. And this story that, you know, something looks hopeless and then some miraculous structure appears that saves you happen over and over and over. So that's why these equations, this new formulation equation is so amazing, right? So a lot of times it's not going to work, there's no reason to work, but there's some miraculous structure that you can only control the term if that term has a special combination of derivatives, and that's exactly the special combination of derivatives that appears in the estimate. Okay, so that happens over and over. So far, so good? Okay. Now, now what happens is that this works, but this in the end gives you control of this guy, right? So this guy will get control. But now when you are going to do, so when you're going to the estimates you're trying to derive are for this equation, which you do, as I said, you take the multipliers, and the connection coefficient that comes out of this equation is this. So the correct coefficient you really need to control is this guy, but the one you can is this guy. So that's why this is called a conformal energy. What you do, you make a conformal change of the metric. Yes, I don't remember what we call it. Such that the null expansion of the conformal guy is exactly the guy we can control. And you do that by choosing the conformal factor appropriately. Okay. Now you cannot do this algebraically. You have to choose the conformal factor to satisfy a PD, right? It has to satisfy a transport equation. Which causes further trouble because now we have to derive estimates for the conformal factor. Okay. And then this is something that you do, again, this is GR, using something called the mass aspect function, which I'm not going to discuss. This is one of the most technical aspects of the argument, but we are lucky enough that a lot of the argument can be traced back to the nonlinear wave equation, the GR. So all you have to do is now to check that they still go through with these extra transport terms. Okay? And in fact, it's not really the mass aspect functions are modifying aspects. All of that. Okay. Okay. So with this, we get okay. With this, I hope I give a taste of how the ideas for the acoustic to control the acoustic geometry go. And I think the message, as I said, these miraculous structures keep happening over and over and over, and that's how the estimate goes. Okay. Then once you have this, if you go back to our bootstrap argument, that was the last element we had here. Then we discuss like how these things are implied by these reductions. We discuss the transport part. Everything comes together, and we close the estimate, so we get this low regularity estimate for the fluid variables. Okay, now so this is all fine and good, but remember, all this is for the classical Euler, right? And this is a course on relativistic Euler. So all this for classical Euler. So what about relativistic Euler? Okay. So lucky enough, Stefan U, according to look at this problem. So Stefan is a very talented graduate student, worked with Jared. So Jared gave to him to do this problem for relativistic Euler, and he was successful. So you can find this paper on archive. And the statement, I'm not reading the full statement, it's just a similar result, low regularity. Result works for relativistic Euler. Now, the important comment here is that you should not take this for granted. Okay, so I think maybe you, again, maybe you can naively think, okay, it works for classical Euler. Now, for the relativistic Euler, you also have this new formulation with the structure. So, okay, there's a motivation, but I want to emphasize that again, the relativistic and the classical problems, there are similarities, but there are many important differences. Okay, so this is not something you should take for granted. Stefan had to work really hard to make this work. There are several aspects I'm not going to discuss. One of them I mentioned before, which is the fact, for example, all your div codes are space-time div codes, right? And just because all these structures, as I hope I was able to use it, are so delicate, even a small thing like that might spoil the whole argument. You have to be very, very careful, right? So you should not take this for granted. This is an important result, okay?
The holder thing is the same thing.
Yeah, yeah. So this is so this is exactly the same kind of signal regularity. Now, as I mentioned yesterday, after we had done ours with the holder, Chan and then Anderson Zhang did removing the holder. So now you can try to do the relativistic Euler without the holder, maybe using Chan's techniques. Okay. So far, so good. Okay. Oh my goodness. Okay. I guess when okay, so I guess when I first sent my summary to Martin, I advertised as applications to shocks, but then later on I decided to put the regularity. So okay, I'm not going to have time to discuss shocks, so I'm going to make just one small comment about shock formation. Okay, so let's because I want to move on to free boundaries. So I make one very small comment about shock formation. And again, the point is how this new formulation of relativistic Euler helps you to study the problem of shocks. Okay. Okay, let me just go to the heart of the matter. It's the following. So the problem of shock formation for Euler, basically what you want to do, you want to have constructive proofs of stable shock formation. What that means? Means you want to have proofs that not because it is known that relativistic Euler solutions for large classes for comprehensive classes of data they break down. That's known. That's the work of Yang and Shadi. But those are proofs by contradiction. They don't reveal the nature of the singularity. So what you want to do, you want to do constructive proofs that reveal the nature of the singularity, particularly the singularity of a shock, which means that the singularity emerges as an intersection of the characteristics, right? So if you remember your baby OD, that's what happens for Berger's equation, and in the end, you're going to show that the same mechanism, intersection of characteristics, is what's going to happen for relativistic Euler. Okay. So you want the proofs to be constructive, and you want the proofs to be stable, because you want this to be valid for an open set of data. Now, again, more of a lot of things I'm discussing. If you go to the heart of the matter, is the following. If you look at the evolution equation for, let's say, let's look at the log, okay? You are seeing alignments for velocity, right? So if you look at the wave equation for this guy, take the wave equation for this guy and decompose in a null frame. So in a null frame, the wave equation is going to look something like this. It's going to be L bar H bar is equal to minus L bar H bar hat plus a null form. Those other terms that are not important. Okay. Now remember, we're trying to prove some type of blow up, right? Now look at this equation here. So if Q is not there, that's the Riccati equation for the transversal derivative of H bar along the integral lines of L. That goes up, just so. So the whole point is that you want to show that these null forms, they don't interact strongly with the high frequencies of your solution in order to distort this blow up. Right? Now the point that you should keep in mind is that Riccati is not stable in the perturbation. Okay, so if you take your Riccati ODE, let's say y dot equal to minus y squared, this goes up. But if you add a small term plus epsilon y cubed, now two things happen. Either the equation still blow up, but at a completely different rate, or the solution exists forever. That depends on the sign of epsilon, don't remember now. Okay, but use it as an exercise. So the blow up of Riccati is not stable under arbitrary perturbations. So what I have to show, that the perturbation given by this null form is really a perturbation, and that's not going to destroy the underlying Riccati evolution to show shocks. Now, That's the case because what happens, and that's the characteristic of the null forms, relative to a null frame, this guy is going to be something that's going to always involve, let's see, so relative to a null frame, your null form is always a combination of general derivative, but a tangential derivative, tangential to the poles. Okay. Now, the philosophy, again, it has to be proven, right? So that's part of the aspect, it has to be proven, but the philosophy of tangential derivatives behave better, right? So from the point of view of these derivatives, this term here is essentially linear. So if you believe that the tangential derivatives behave better, that you can control the tangential derivatives, then this guy is linear. And then it's not going to spoil the recap. Okay? So that's the heart of the argument for the pseudo-Fock formation. And for that, null forms are crucial. Before, for the role of relativity, you just need this to that. Here has to be a null form. So if you want to do the shock formation and you don't have the null forms, then this argument breaks down. Okay? Okay, so that's on my like 5-minute lecture on shocks. But I need to point out the following. This hasn't been done. Okay, so this paper hasn't been written. So what I'm telling you now, that's the framework that we have available for the study of shocks. That's what Jared used in his book for quasi-linear wave equation not satisfying the node structure. That's what they use, Jared and Jonathan using their work for the classical wires. But for relativistic wire, this hasn't been done. All I'm pointing out is that if you want to use the same kind of structures that are present in these other works, then the structures are there. The new formulation of the equations they have these structures, but this has to be proven. Right? Nobody has done this. Okay, so this is still kind of.
Is this being worked on?
Not that I know of. Okay. Okay, so modulo a zillion things that I didn't tell you. That was my 5-minute lecture on shocks. So I guess we can take a break, and then we can come back and talk about something else. Okay, so we are back. We're going to keep talking about relativistic Euler. So we're going to talk about relativistic Euler physical background. So what does that mean? Okay? So the idea is the following. Suppose you have a fluid contained in a region, but the region is not fixed. It's not like a glass. The region, the region moves with the fluid. So I say this is a time 0, and then at a later time, I say time 1, like this. But it's moving with the fluid. It's not like you're not prescribing how to move. For example, a liquid drop. A liquid drop is like this. And maybe more important for the case of relativity, a star, right? So a star, that's what a star is doing, right? So its boundaries moving the fluid. So fluids of this type are called free boundary fluids. So if denoted by omega sub t, so this is the region containing the fluid. At time t, so let's say so these are omega t then. The moving domain is where the dynamics takes place is going to be simply the union of a certain time of omega t. Okay. So the idea is that this is the time direction. So we start here with omega 0. Then I don't know at omega t1, omega t2. The dynamics then defining this region that you know it's cylinder, it's like a cylinder topologically, right? Okay. And so this is the moving domain, and then the free boundary is the same thing, gamma, and the union of the boundary. Okay. So as you can imagine, the difficulty here is that different than a standard initial boundary value problem, you don't know a priori what the domain is, right? The domain where the equations are defined itself depends on the solution. So that has to be determined alongside with the solution itself, right? So you have to find now you have to find the velocity, the density, possibly the entropy, but the domain itself, right? That's a difficulty. Okay. So in particular, if you look at the relativistic order equations, now because we have this boundary, there are some boundary conditions. Okay? So there are boundary conditions. And the first boundary condition is that the pressure on the boundary has to be zero. Okay, so that's coming from physics. Okay, that's coming from physics. That the pressure on the boundary is zero, but you also have the condition that the velocity has to be tangent to the boundary. Okay, so this is just there's a tangent space of the boundary. So this is simply saying that the fluid, the boundary fluids are advected. Okay, so the boundaries are advected by the fluid. Right. Okay. So the second condition is kinematic in nature. So this is simply saying that if you look, okay. So if you have a fluid particle on the boundary, right? So how the fluid particle on the boundary is going to move? Well, it's still part of the fluid particle, so it's moving the velocity of the fluid, right? So therefore, the boundary is moving the velocity of the fluid. That's basically what this is, right? That's the setup. So we want to study the relativistic order equation setup, and we're going to assume from now on we have a barotropic fluid, which means that we're going to assume that the pressure is a function of the density. Okay, so we're not going to discuss the case where we have that. Now, because the pressure is on the boundary, and if the pressure is a function of the density, this gives you a condition for the density of the boundary, right? And at this point, there are two possible cases that we're going to distinguish. There are two cases. The first one is called a liquid. And that's the case where the density is bounded away from zero on the boundary. This is the density of the boundary. And the second is the case of a gas, where the density is zero on the boundary. And I think the names liquid and gas are more or less self-explanatory, right? But the important thing, of course, in both cases, the pressure is zero, right? Both cases, the pressure is zero. But the important remark is that not only they correspond to different physical situations, mathematically, these problems are very different as well. So the techniques here used to the liquid are not the same for the gas. The functional framework is not quite the same. In fact, it's very different. So, so here we're going to pick one. We're going to study the case of a gas. In this case, the boundary is also called a vacuum boundary.
Very broadly, which of the two is more understood?
Okay, I think, so first of all, relativistic, both are fully understood. Classically, I think that if you were to judge in terms of the size of the community and the number of applications, the liquid, I would say, is better understood. Now, if you have a liquid, classically, then you can also consider the case with surface tension, right? Which the mechanism keeps the cohesion, or let's say, which the surface tension is basically, so they have a boundary condition then where the pressure on the boundary is going to be equal to the mean curvature, right? So then in the liquid, there are two possibilities. You can have the pressure equal to 0, but you can also have the pressure equal to the mean curvature. The case of the mean curvature is a little less studied in the case of 0, but both, I think, are better understood in the case of the gas. Relativistic, then not much known in either case. There are some results for the liquid. And for gas, as far as I know, results is the very first one. Okay. Now, so we consider a gas, and then in the case of a gas, it's not difficult to characterize what the moving domain is. In the case of a gas now, going for a gas. Right, so omega t is simply the set of points where the density is positive. Okay. Now another condition that we have for a gas is the following. We are going to also assume that the sound speed is going to vary from the boundary. Right? So this is simply telling that sound waves cannot propagate into vacuum across the region where the medium vanishes. Right. So that's the setup. And finally, we're going to pick an equation of state. So the equation of state that is typically used in this problem is a power law, where k is greater than 1. Okay. So k is greater than 0. Right, so k cannot be 0 because then if it's linear, the sound speed cannot rise for the constant. That's now what is interesting in this problem is that not only the sound speed is 0 on the boundary, but the decay rate of the sound speed matters. The decay rate of sound speed matters. And for this, let's do some heuristic argument. Okay? Let's take the sound speed squared. Okay, so of course, if you write square, but square is better for the computations. Let's take the case where the sound speed squared is comparable to the distance to a power. So here is the distance to the boundary. So why that? Well, just because the distance of the boundary is like the natural scale of this problem, right? Because everything away from the boundary where the density is positive, you can just localize the problem using finite propagation speed, and you have plain volume. So like the distance of the boundary is really the important scale. Alternatively, you can imagine doing a Taylor extension near the boundary, right? And then if you just look at the first non-vanishing term in the distance, right? So you can take something like that. And now let's compute the form acceleration, right? Which is u mu d mu alpha, which you know is minus cs squared by alpha u d mu rho divided by d mu. Okay. So remember, it's the derivative of the pressure, but the pressure density together the sound speed, right? So so basically, this is telling this is going like what? Going like CS squared, one derivative of the density divided by P plus rho. But P is rho to the kappa plus 1. And kappa, kappa is greater than 0. So this guy decays faster than this guy. So here I can just keep rho. Okay. And then now what you can do, you can just so using this condition and using the fact that this is like rho to the k, right? Because one is right. So we have that then rho. So rho is like what? Rho is like d to the beta over k, right? So this whole thing then is what? CS squared is d to the beta. D rho, okay. D rho is going to be what? It's going to be d to the beta k minus 1, derivative of distance, divided by d beta over k. Derivative of the distance is order 1, right? It's like dx. And then, let's see, what happens here, if I do this correctly, you should get distance to the beta minus 1. Right? So this guy is cancelled. Now, this is the acceleration, right? So this is telling that this is going to be what? This is going to be 0 if beta is greater than 1. It's going to be finite if beta is equal to 1. And it's going to be infinite if beta is less than 1. So that tells you that of the possible decay rates of the sound speed squared near the boundary, the only one that's physical is beta equal to 1. This one gives an infinite acceleration. That's not physical, right? This one gives you 0 acceleration. Okay, that's sort of physical, but doesn't cover any important. Think of a star, it's rotating, right? So the acceleration cannot be 0, right? So any interesting physical system is going to have acceleration of the boundary, right? Simply the particles are moving linearly with the outer speed. Okay, so that tells you that if you want to study interesting systems, you should take that decay rate. Okay? People wrote papers, decay is beta greater than 1. But what happens is that, again, not only that's not very physical, as you're going to see from our estimates, in this case, things become simpler. The whole point is that, because of the degeneracy on the boundary, we have to use certain weights, and the weights are going to be given by this. But if this power is very large, basically the weight kills every dynamics on the boundary, right? So all the estimates. So if you take beta equal to 1, you can even couple twice and solve this problem. Okay, that has been done, but that's not the case with our. Okay, so so this leaves the following condition. So we're going to from now on assume that this guy is going to be comparable to the distance to the boundary.
When you have a different equation of state, this picture like changes completely, or
no? Just okay. I shouldn't say that for every equation of states is going to be the same, but for the reasonable equation of states that people use, something similar. Okay. Just the heuristics here is much simpler because we just count power. Then you have to do something more complicated. Okay, so we're going to assume this. So this is called the physical vacuum boundary condition. So this is a condition we're going to assume. And the way you should think of this is a constraint. This is something to impose on initial data, then it's propagated. Okay, so think of it like a constraint. Impose on initial data, then it's propagated. And then what are the relativistic coordinate equations of physical vacuum boundary? They are the relativistic coordinate equations when you have this condition. Okay, so that's the problem we want to study. Okay. So, so let me tell you briefly what the static is going to be to study this problem. So first, we're going to find some good nonlinear variables. That diagonalize the problem with respect to the material derivative. The material derivative is going to be dt plus ui u0 di. Okay, so this is just the u derivative, right? The u derivative is u mu du. But for technical reasons, which involve, in particular, some commentators, you want to have a coefficient 1 here on the dt derivative. So you divide by u0. And the reason why you want to solve, so remember, the relativistic order equations, they have time derivatives appearing in both terms, right? Because they have the d mu p here, this involves also time derivative. You want to have something which is always on the form dt equal to something only spatial. And the reason because our proof in the end we're going to apply some Euler method. And Euler method you always like to write dt equal to something only spatial derivatives to do an iteration, right? That's why you want to diagonalize the system. Then the other thing you're going to need some good linear variables. A crucial aspect of our approach is that the linearized equation plays a central role. And the reason is that what we're going to show, we're going to differentiate the equation with respect of several material derivatives with nonlinear variables. And you want to show that this guy here satisfies the linearized equation with some good perturbative terms. And then the third aspect, you have to put everything together. Then you use like regularization of arguments to construct solutions, right? So I'm not going to discuss much of this, but I want to discuss these two aspects. So let's say these two aspects basically are energy estimates. And then there is the actual construction of solution that I'm not going to discuss much, but I hope that we just get to the energy estimates so we can have an idea about stuff. And we're going to assume from now on, like we did before, for the new formulation, the Minkowski. This is okay. Again, all the difficulties are present on the Minkowski case already. There's no point of making our life harder. Okay, so here's how this is going to go. So first, let me discuss stabilization. So what we're going to do, we're going to construct a new vector field that's going to be a certain rescale of the velocity, and I'm going to choose this function f appropriately. Okay. So if I look at the equation satisfied by this equation phi now, it's going to be the following: it will be d plus rho divided by f mu d I CS squared GI mu rho plus minus f prime divided by f equals rho plus CS squared I mu rho equals 0. So just use the equation of motion to derive the equation for V. And here I'm already writing only for the spatial components of V because they're constrained, right? So I can write, so the constraint out is V naught squared minus F squared, right? So I know the VIs, I know V0. So I can write on the form. So I want my equations to be diagonal with respect to the material derivative. So this guy here, up to a multiple, is the material derivative. So I can just multiply by something. This guy is good because since I'm looking only at the VI components, this matrix diagonal, so this guy involves only spatial derivatives. But this guy is bad because there is a material derivative here. So I want to kill this term. So I just choose F. Let's get this guy 0. Okay. So if you just integrate this equation, that tells that F has to be e to the integral of CS squared of rho divided by equals rho 0. So this choice of F kills that term. Okay. Now something interesting happens. So if you have ever worked with relativistic equations before, this function is something you should recognize. Okay? Because if you have a barotropic fluid, remember we define the vorticity as d of a u. But for a barotropic fluid, there is an alternative definition you can take for the vorticity, which is the following. You can take only for a barotropic fluid. You can take omega to be d of f times u. And why is that a good definition? Because this guy here now is going to satisfy the Lie derivative of omega equal to 0. Okay? So again, whatever you call for this is something you want to satisfy a transport equation, right? And this definition has the advantage it satisfies a homogeneous transport equation that you can use for estimates. For a barotropic fluid, it's more convenient to use this definition. Moreover, this definition here is automatically orthogonal to U. It's automatically orthogonal to U. So this tells that using this equation, we can write the 0 j components of the vorticity. We can write in terms of the ij components, plug back here, so we get an equation only for the spatial components of the vorticity. Okay? And why it's important? It's important because our equation for V is going to be an equation only for the spatial components. So in the end, we're going to recast everything only in terms of the spatial components. And the 0 components is always get by the constraint. Okay? Okay, so now I make an observation. Everything that I'm going to say from now on, it's not going to be exactly true. Everything I'm going to say from now on is going to be true modulo estimates for the vorticity. Okay, just because I don't want to spend time discussing estimates for the vorticity, because estimates for the vorticity are going to just be old-fashioned transport estimates. But in the end, the estimates I'm going to show to you are going to give control over rho in the divergence part of U. So the divergence part of V. To get full control of V, you have to control its divergence part and its curl part. So this is like the curve, right? So everything has to be complemented by transport for the vortices, but I'm not going to mention that. I'm going to mention this once. Just keep in the back of your mind, everything I'm going to say from now on has to be complemented by this further transport estimates. Okay? So in other words, in the previous problem we discussed, the transport was the key that I want to really discuss, because it was the new element. Now the transport is the part that doesn't matter very much. Okay? Okay, so in the end, so we have this definition, right? Now in our case, remember P is a power law, so we can plug this here and integrate. And in the end, you get the following evolution equations. I'm going to tell you what R is in a second. Okay, so first of all, what is R? So R is k plus 1 divided by k, go to the k. So this is just a sound speed. Okay, sound speed is this, right? But just convenient to divide by k. And this is natural because I told you the sound speed is this very important quantity in the problem because it's comparable to the distance. So it's natural to recast the equations in terms of the sound speed, right? And just for convenience, I divide by k. Now here, G is the following inverse Riemann metric. Okay, this is going to be something complicated, but I'm just write the expression. And this A0 is equal to 1 minus CS squared I divided by square. So G is this complicated inverse Riemann metric, which is related to the acoustical metric. It's not exactly acoustical metric, cannot be because the acoustical metric involves C factors that are zero on the boundary, right? But it's related. Okay, it's related to the acoustical metric. In particular, this operator is like a divergence, right? It's a divergence, as I said. And finally, then you have these coefficients A1 and A2. I'm not going to tell what they are. All you need to know is they're like order 1. They are smooth function of the variables. And the only thing you need to know is that A2 is positive. The sign of A2 is not negative. Okay? So those are the equations you want to study. So what I need to tell you next is the kind of function space we're going to use. We talk about function spaces. Okay, so let me define the following norm. Where is the integral? Okay. So first, what is this? So this is like an L2 norm, right? The L2 norm of W, the L2 norm of S, but with some weights, right? We're working on a degenerate problem because it's degenerate on the boundary, right? So it's natural to consider weights. But why this specific form is because I'm going to show you later. This energy, this is the energy for the linearized equation. So if you look at, if you write an energy that you can bound like E of t less than E of 0 for the linearized equation, that's the guy that you're going to control. So this is the energy for the linearized equation. So it's like a weighted L2 energy. And now you want to define higher order spaces. And then the question is how to do that. And here's the idea. Remember, underlying the equation, there is a wave evolution. There is a wave equation underlying. And the wave equation is like two material derivatives minus the sound speed Laplacian, right? So this suggests to construct spaces based on powers of this operator. Because your spaces should involve only spatial derivatives, right? So we can define the following spaces. This is going to be W by H2L squared. So this is going to be the sum alpha from 0 to L. The sum from 0 to L, where alpha minus J is natural. And then we're going to take R to the 1 minus K divided by 2K plus A times D alpha S D R to the 1/2 D alpha. I'm going to take now 2 squared. Okay. This looks complicated, right? But let me explain what's going on, right? Forget about all the sums. Just look at what's happening at the highest order, okay? At highest order, okay, so an alpha is equal to 2L, right? So this term here is going to give you what? We're going to have R to the 1 minus K divided by K, then plus L, and then we're going to have, sorry, there's a 2 here, right? We're going to have 2L derivatives of S. This guy is L2, right? But this is precisely what you get if you look at this guy here applied to S in this norm. This factor here, there are 2 here because I'm putting inside L2, right? So there's the square. This factor is this guy. I have 2L derivatives, right? So if you raise this guy to the power L, it's 2L derivatives. And then I have an R to the L, which comes from raising this guy. And here's the same thing, except there's an extra factor of half here because this guy has an extra factor of R. Okay, that's what's going on. So these are like the function spaces that are not considered. And then let's see. I need to introduce a few more norms, then I can state the result. So I need to talk about some control norms. So let me introduce the following pointwise norms. I'm going to explain what this means in a second. This is going to be so we're going to do an energy estimate. So we have some control norms, but like the knowledge you get when you run all things, right? It's like before, was the L1 in time and infinity space, right? So here there will be something more complicated. They're going to involve these 2 guys A and B. So this is just the Holder semi-norm. I'm going to tell you this in a second. Now, what is N? N is the following. So consider your boundary, okay? So consider your boundary, S2 sub T, and pick a point on the boundary, X0, okay? Then I can look at the gradient of R, this point, and I can construct a vector field N such that at that point N is exactly equal to the gradient, and then it's going to be something, I don't know, close by, okay? I can also construct something like that. Now, why is this construction important? The idea is that, again, this is a hyperbolic problem. So in the end, I can localize everything in the neighborhood of R. Okay? So in our arguments, we're going to be implicitly assuming that you're always working in the neighborhood of a point of the boundary. Away from the boundary, the sums in this boundary from below, you can just do estimates using plain old, I don't know, symmetric hyperbolic system. So all the business, all the issues are near the boundary. Then near the boundary, I can localize in these small balls. And then I can always construct such an N. And that's important because in the end, with my control norms, I want to make this guy small. I want to make this guy small. And if I don't have this, I cannot make the gradient of R small just by localization or scaling arguments. So this quantity gradient of R in our function of framework turns out to be scale invariant. Now, I didn't tell you what the scale is for this problem. I'm going to skip that. There is a way of talking about the scaling of the problem. And this guy is going to be scaling that. So that's why I have to subtract this. Now, here, this C tilde, the C tilde norm is defined as follows. So if you look at the C tilde 1/2, the two x, y, and t, y, f of x minus f of y, then r of x plus r of y, plus x minus y and a half. So if you didn't have this guy, this tilde would be simply the Holder seminorm. So this is like the Holder seminorm, except away from the boundary, this guy is positive, so it's weaker. So it's like the Holder seminorm, but away from the boundary, you don't. See, this would be like 3 derivatives, right? But away from the boundary, you have one less because, right? Because this guy is positive. So this is like the whole. So essentially, you can think that this guy here essentially is like 3/2. Okay, but it's like weaker. It's weaker than 3/2. Okay. I have all the ingredients that I need now to state the main theorem. So this is joint work with Einstein. So then consider again the equations. R plus R minus 1, J plus R I 0 I 0. So this is of course defined in omega, where omega is above, right? So the domain, the union of domains where it is positive. Let's define this state space. The set of guys such that for each time they belong to our correct vector space. The statement then is that these equations are locally well posed in this space if the initial data has the same regularity. And finally, the condition of irregularity, which is 2L greater than 2L plus 1, where 2L is equal to 3 plus 1 plus 1 over 2. Let me explain this. So you have your equation of motion, right? So we want to show that there exists a solution unique, and so on in some space. And a space to consider is just a space of all R's and V's, such that for each time they are in this weighted solid spaces that are defined before. Okay. So for them, for a solution to exist, of course, the data has to be the correct space. It satisfies the physical vacuum boundary condition, right? So the domain time is 0 is the set of points for the density. The sound speed is positive, but the sound speed is positive, the same set of the density is positive. It's compared to the distance. Sorry, the sound speed is square, right? But then there is this condition here, which tells you that you need some regularity, right? You need some regularity, right, for your solutions. And the regularity is given in terms of this L naught that I'm defining here, and I'm not telling you where this is coming from, but the whole point here is that this guy here is the critical. This is the critical. Well, K naught, right? So L naught is the critical space. You know, when you do scaling analysis on an equation, you can identify critical spaces, which are, let's say, the cutoff spaces below which you expect you should not get local opposedness. I didn't tell you what the scaling is for this problem, but there is a way of identifying one. And then you can identify the critical spaces, and these are our critical spaces. Okay. So in particular, this means that you get solutions L greater than L naught plus a half, right? So that tells us that this is very low regularity. It's only half derivative above scaling. Okay. Now, first, to do that, this number doesn't have to be an integer, right? We have to define this space for non-integer. But you can do that with interpolation. I define only for integer values, but with interpolation, you can define for non-integer. Then you can talk about these fractional values. And here, local opposedness really means the full local opposedness in the Hadamard sense. We get local existence, local uniqueness, and continuous depends on the data. Okay. Now, continuous depends on the data is a bit tricky because we have to compare two solutions. But two solutions are defined in different domains, right? So if you have one, remember, a solution, a domain here, another solution, a different domain. So we have to put a topology on this space, which allows you to compare solutions defined in different domains. I'm not going to tell you how to do that, but the basic idea is that you have two of these domains in that Minicourse space. You can compare the distance between their boundaries, right? You can compare the distance between the boundaries. And in more, but that's not the basic. Okay, that's the theorem. And then after that, okay, so the second theorem is a continuation criterion. I'm going to state this briefly and say more in words. Basically, we construct some energies that are comparable to the norms. Okay. And these energies satisfy, well, they are energies, like I call them energies, they satisfy energy estimates. And the crucial thing is that here, remember the control norm B, so it appears as a linear factor of the control norm. That means that you can run all this. And this gives a continuation criteria. It tells that you can continue the solution as long as this guy here is finite. Right? So you get a continuation criteria saying that you can continue the solution as long as B belongs to L1T of a map. Right? So that's a continuation criteria. And remember, B basically involves that C tilde half norm, right? But in terms of velocity, is the gradient of the velocity at infinity. So for this rebounding problem, we get pretty much the same continuation criteria that we have for standard classical Euler. Okay. Okay. So those are the theorems, and so what I'm going to do for probably the rest of today is just trying to give a few ideas of how this is moving. Okay, so and everything goes to basically linearize the equation. So if you look at the linearized equation, So think of here that S is the linearized variable associated with R, and W is the linearized variable associated with T. And then you can compute the linearized equations. So I'm going to get something like this. Give some source term. And here you're going to get S. Okay. So let's say you want to do energy assets for this guy. Okay. So what you're going to do, we're going to multiply this by S, and you try to contract this with W, right? Now the first thing you want to do, because I have this A2 here, I'm going to divide by A2, which I can, because remember A2 is positive. Okay. Now if you do this, here you're going to get some dts squared, here you're going to get some dtw squared, but then here you have some cross terms. Here you have W times S, derivative of W times S, and here you have derivative of S times W. We want to cancel the cross term, right? So this is going to be an estimate for the undifferentiated variable, so you need to cancel the derivatives. Okay. Now the first thing you need to realize that to cancel derivatives, this term here, W, derivative of W times S, has a G and has an R, right? So the corresponding term from here, which is W times derivative of S, doesn't have a G and doesn't have an R. So I have to put an R and a G here. Okay? So we have to, in fact, contract this with R, G minus 1, G minus 1 J, WJ. And then if you do that, what you're going to get R, G minus 1 J, DI WJ times S. And then when you add this equation here, the A2 you divide by, so you're going to get R, G minus 1 IJ, WJ times DIS. And now this and this, the perfect derivative, right? So you can write those guys as R, G minus 1 J, DI, WJ, S. Okay? And then this time here, we're going to integrate by parts. Okay? But then there's a problem. So if you look at the energy that comes from this term here, right? The energy comes from this term here is going to be something that's going to be what? It's going to be R W squared in this norm, right? So the energy has an R. And remember, R is going to 0. So when you integrate by parts this derivative, you're going to hit this guy. Derivative of R is order 1. So you cannot control this term after integrating by parts by this part of the energy, right? There's no way, because this is going to 0, and this is like a 40. Now what happens, you do have the term where the derivative hits this R is appearing here. So what you want to do, you want to cancel this term with this guy. Now this guy has 1 over K. If K is 1, you are done. If K is not 1, it means that you have to multiply these equations still with some power of K. Because then when you multiply with powers of K, this guy here can be written as a derivative of R to K to a power. And the power turns out to be exactly the ones that I told you those energies. Okay, that's why you have those terms, just to get that conservation. Okay? So the crucial message here is that, you see, if you look at these equations here, and you want to derive estimates for S and W, you would think that this guy is a lower order term because it has no derivative of the vectors, right? So you just have to cancel the derivatives. But to cancel derivatives, because you have a weight, this term is not lower order term. And this term, example, this term is coming from your linearized equation. This term is coming from the linearization of the T. Because the T has a VI over V naught. And what is not trivial to see, but what happens, that when you linearize this term, what pops out is precisely that metric. Okay, that comes from the structure of the metric. Okay, so when you linearize, that guy pops out the metric. Okay. So there is this sort of special cancellation that happens. Now this is possible only, right, because now your energy has this R plus these R's here. Now these R's are fine because they're multiplying the equation by them, right? But what you need that the source terms have the same powers of R. Okay? And they do. You have to go back to the linearization and verify that these guys, in fact, they have all the correct powers of R to be controlled by the energy. So that's the whole business that you are going to play in this game. Everything boils down to estimates. But your energies are weighted. So if you have some term that's missing a power of R, you cannot control. So what in the standard problem are just coefficients, the sound speed square is just a coefficient. It's just a point on a constant. Now you have to take care of that. You have to be very, very careful with all these powers of R because they matter. Okay. So then the next thing that you want to do, of course, this is just the first estimate for the linearized equation. Okay. You want to derive now higher order estimates. And how do you derive higher order estimates? Well, again, you differentiate the equation, right? And do the same estimate that you did for the linearized equation, you're going to do now for the derivatives, right? But you need to learn a problem. If you start taking derivatives of this equation, you're going to start hitting derivatives of the coefficients. Okay? Now, because you have this business that the powers of R matter, if you take a derivative of R, you are losing a power. The derivative of R is basically order 1. So you have to do all this now and make sure that when you take derivatives, you're not going to miss any power of R upon differentiating these guys. And that, in principle, cannot be done with arbitrary derivatives. However, if you take derivatives of these equations, you take only dt derivatives, what happens? Every time that a dt hits R, you can use the equation. Remember, the equation is like dtr plus r g minus 1 ij diw j diwj plus r a1 di r. So this guy has a factor of R, this guy has a factor of R. So every time that you hit the derivative of R, you gain back R with a factor of R and V, which then you're going to put, let's say, at infinity, because you're going to be part of those control marks. So that tells you you are allowed to differentiate the equation with respect to the material derivatives. And then you have to do an extra argument, which will involve elliptic estimates to control the full derivatives. Okay? So what you'd like to say then, you'd like to derive estimates for material derivatives of R and material derivatives of V. So these are going to be your variables now. These are going to be your variables, so you're going to treat them. And you want to show that these guys satisfy the linearized equation, because for the linearized equation, you already have the basic L2 estimate with perturbative terms that you can control. So that's the basic idea. Based on this argument, you can take derivatives with respect to the material derivative. However, This doesn't work. And the reason why this doesn't work is the following. If we start with the initial equation and take a dt, dt commutes with itself, right? And this key term that you need for the cancellation came precisely from the fact that a regular derivative does not commute with dt. It came from the linearization of this guy, right? So if you take a dt, this term is not going to appear, and then you cannot get the cancellation. Okay, you cannot get the cancellation. So this is not going to quite work. So, so what we're going to do, we're doing something slightly different. Okay, we're going to define some new variables, S and Wn, which are the following. Wn is exactly the n material division of V, because for the V equation, you don't need that term, right? So that term is something on the equation that you linearize for R. But then for the R guy, you're going to say that this is what you thought was the correct thing, and then that other term, you're going to put it by hand. Okay, you're going to put there's going to be some coefficient here. But then in the end, you're going to put this G minus 1, Ij, dir, dt minus 1, dj. Okay? So this guy here, you're defining these new variables precisely with the extra term that you need to cancel. You see, here you have, so this guy here has always one less derivative in the top order you're trying to estimate. So here, if you're trying to estimate the nth material derivative, this guy here is going to be n minus 1. Okay. So you define these variables, and then you take dt of these variables, and you show that with these definitions, these equations satisfy the linearized equation, right? Because now you put by hand this guy. See, when you take a dt of this guy, you hit a dt here, and dn of v is precisely W. Okay. Then that gives you the correct variables. This is only valid for large n. For small n, you have to modify a little bit. That's a small technical thing that I'm not going to discuss. But that's kind of the basic idea. Okay. So the big idea here, basically, is the following. The big idea is that we want to refer everything back to the linearized equation. Linearized. In particular, that means that you want to find good linear variables or linearized variables which are these ones that solve the linearized equation with good perturbative terms. That's what this course is gonna do. Okay. So now we basically have the framework that we need to derive energy estimates. Okay. So I'm going to talk about this, and then talk about this, talk about this. Yeah. Okay, so here's the important thing now. Okay, now that we have this linearized variables, I'm going to define my energy, which is going to be basically the sum up to L of these variables S2J, W2J, evaluated on the basic norm. There are two norms for the linearized equation. Okay? So basically what's happening here is that, okay, so let me explain what's happening. So if you look at these variables, let's look at, for example, S2, look at say S2J, okay? This is basically 2J derivatives, material derivatives of R, plus a correction that you need. But let's forget about the correction, right? So if you didn't need a correction, then again, that was our initial guess, but then you need the correction. Okay? Now, so this is saying that S2J is basically dt2J of R. Now remember, every time that you take a material derivative of R, you gain an R back, right? So if you iterate this using the equations, this is going to be basically, so you're going to get something that's going to involve, so if you look at this guy here as 2J in H, this is basically like R to the R to the J, the 2J of R evaluated in L2, which is basically like our R age 2J more. Okay, so the idea is that so we're casting things here in terms of these linearized variables, but again, if you ignore like other terms, if you just look at this, if you just count derivatives, that's basically sort of the norm that you're trying to control, right? Okay. So this will be the L. So this has the weight 1 minus k divided by k. Okay, so that's kind of the basic picture of what's going on. So that's the correct energy that you want to control. But of course, you have to show that this is in fact true. You have to show that these norms for these linearized variables in fact control the norms that I defined before. So you have to actually prove this. In other words, you have to show that these energies coercive. Okay? That's what you want to show. You want to show that these energies here are coercive. Right? So you want to show that this guy here is comparable to R V H 2J square. Get the square here. Okay. Okay, so to prove this, okay, so I'm going to show it, it's equivalent, right? So you have to first show one inequality, then the other, okay? Now this one, none of them is easy, but this one is, let's say, the easiest. Because you start with these variables, you write their definition, do a bunch of triangle inequalities, and then you have to show that it's controlled by this norm. Okay? So what you have to do here, you have to basically count derivatives. But because in the end, your final norm does not involve time derivatives, right? So you have to use the equations to recursively solve for the time derivatives in terms of the spatial derivatives. So when you do that, you're going to get some complicated multilinear expressions, right? Because you keep solving these, keep getting problems. So to handle those multilinear expressions, you have to do some interpolation. But the whole point here is this is not your plain vanilla interpolation because you have all these weights. So you have to do some weighted interpolations. So for this, there are some powerful interpolation theorems that were developed by Mihail and Daniel in a previous work where they treated the classical way. Okay, so here we just quote from their paper. There's some. So the one you're done to make is like you count derivatives, you interpolate, but this is not your old-fashioned vanilla interpolation because of the weights. There are some powerful interpolation theorems that Daniel and Hal developed, and that's what you use to handle this inequality. Okay? So what I'm going to show to you is the equivalence. I'm going to show you the other inequality. Okay? That's an inequality I want to show. Okay. Let me this. Okay. So what I'm going to do, I'm going to use some kind of recurrence relations. And from now on, for simplicity, I'm going to discuss only the variable s. Everything I'm going to say can be done similar for the variable w. Okay. So there are some recurrence relations with relating the variables at the level 2j with the variable at the level 2j minus 2. And where is this coming from? So it's easy to see where this comes from because if you look at the equation, let's say dtr, this is like r dv, right? That is the g. And then what you do, you derive a wave equation by taking dt to r, this is like r d, but dtv is like dr, so dt to r is like r dt to r, right? And this is the wave equation for the density, right? So this is the wave equation for the density. But now, if you apply 2j material derivatives to the equation, what do you get? Here you get dt 2j plus 2 of r, and this is like r, a second derivative of dt 2j of r. Now this guy, again, modulo some correction terms that you have to worry about, but this guy is basically our variable s 2j, and this guy is basically our variable s 2j plus 2, and here we have a second order operator. Okay? Second order. And you can write precisely what the second order operator is. Let me tell you what it is. So the operator L1 of f is defined as A2 b minus 1 of j r b j s plus 1 over k ir bjs. Okay? Now, this is really the operator. If you write a wave equation, this is the second order operator that appears. Before I told you, the wave equation is like this, right? But this is like an oversimplification, right? So it's not going to be the flat Laplacian that's going to appear. It's going to be something involving this FGG. And if you write carefully, that's precisely the guys that appears, which is desirable, right? Desirable is coming from the wave equation. Okay? And then the whole point is show that this operator is going to be an elliptic operator. So remember, I told you the philosophy is like you want to take dt derivatives of the equation, material derivatives, but to control the full derivatives, then you do some elliptic aspects. So that's why the elliptic is going to be. But for this operator satisfies some elliptic aspects. Okay? So here's what I want to prove. There's going to be some lemma. We want to show that if you look at the AG2 norm, 1, 2k plus 1/2, and I'm going to tell you what this is in a second. L1s, AG0, 1, 2k minus 1/2. Plus, you know when you do a testing, there's always a lower order term. It's like the L2 guy that you're not going to care about. Okay. Where this guy is simply in general, I can define the following weighted Sobolev space. You can simply sum this guy elastic S, R to the sigma, d alpha F, now square. This is just a standard Sobolev space. And what is the relation between this space and our curly ages? Well, they're equivalent. So turns out that this age 2j is equivalent to age 2j 1 minus k divided by k, so that is 2k j plus the same thing for the velocity. The velocity has a close half. I'm ignoring the velocity here. So this norm here is the norm that we want, but it's equivalent to our curly age. So in fact, the curly age and this norm at top order they are exactly the same. Okay. The only difference is the curly age, the power here changes, whereas for the standard weighted Sobolev norm is always the same power. But just using embedding of weighted spaces, you can show that they are equivalent. Okay. This is just plain old-fashioned embedding of weighted spaces. Okay. So that's the estimate you want to work. And now, to prove this estimate, it turns out that if you just do integration by parts, you get the following Winkel estimate. So this is just direct integration by parts. The following Winkel estimate holds. Plus S H1 over 2k minus 1. Okay, so what's happening here? So forget about the weights for a second. So this is like an elliptic estimate, second order operator in L2 controlling two derivatives. Right? And then, like you're doing standard elliptic estimates, you can sort of first get a weaker and a positive just by integration by parts, where you say that second order operator in L2 control two derivatives of the solution, but then you have a term here with one derivative. So now I have to control this term with one derivative in terms of your operator. Right? So this is like the same logic you do for ordinary elliptic estimates, now that you have the weights. So everything now is reduced to show that this norm is controlled by L1 of S. Okay. So to do this, so here's what you're going to do. Okay. Let's look at the integral negative of R 1 minus k divided by k. This is the ordinary derivative in the third direction of S times L of S. So let's write what this is, just using the definition of R1 that I just replaced. This is R 1 minus k. With the S, we have G minus 1, 2, R, dr, djs, plus 1 over k, R, djs. What we're going to do, we're going to take this guy here, we're going to integrate by parts. Okay? So if you integrate by parts, there is one term that is this guy. Right? So this is going to be equal to the 1 over. Let me write and explain what it does. Okay. S Q minus 1 by J djs 2 minus. I really need to write all the terms here because there is some consolation that needs to be used. So let me write and explain let me just unknown. Let's see. So the derivative are parts. So there's one term where the derivative hits this guy. That term is here, okay? And then that term, there is an r to the 1 minus k divided by k. There's an extra r here that gives our r1 over k. Okay? And all the other terms, so it's just this guy times this guy. Now, this guy times this guy, I did not. Okay, so this guy times that is here. Okay, all it is multiplied. Now, when you integrate by parts, this guy, right? Sorry, integrate by parts, this guy. So there is one time the derivative hits this. Now, the time the derivative hits this, I do like this. First, before integration by parts, I combine this, and that gives a r1 to the k. Then I integrate by parts. When the derivative hits this guy, I get 1 over k minus 1 derivative of r. Okay, so this, so then this guy, and then finally there's a term of the derivative hits these coefficients, g and h. Now observe that this term that comes from the derivative hits the green guy exactly cancels the one with the blue. Okay? And I need that because you see the S that I'm trying to control one derivative of S. These terms they are quadratic in one derivative of S, but they don't have any sign. So yeah, this guy and this guy, right? So these two guys cancel. Okay. Now, here, this term, I can use the fact that Gij is symmetric. I can write as 1/2 d3 of g minus 1 ij bis bjs, right? Right like that. And then these d3 integrate by parts again. Then we integrated this, when integrated this d3 by parts, it's going to hit this guy. And then instead, that guy is going to give what? We're going to give r 1 minus k divided by k d3r. Okay? And then here comes the thing. Remember what I told you about the fact that I can write this. Remember I told you that you can take our vector, the vector field n, which is equal to r at a point. Here's what I'm going to use. Right? I can adjust my coordinates such that this vector field n is, let's say, 0, 0, 1. I take a frame near the boundary where that's the case. That tells me that the gradient of r is essentially 0, 0, 1. In particular, the third component is positive. So this guy here is greater or equal than, I don't know, a half. Right? So this term here is forcing, because now this, after I remove derivative, this is a bilinear, positive bilinear form, right? So this is just ds squared. This guy is positive. So this whole thing here, this whole term, bounds from above r to the 1 minus kk ds squared, which is what I want to control. Okay? And then there is this guy here, But see, the one that I want to control is r to the 1 minus k divided by k. So there's an extra power of r here. So this guy doesn't have a sign, but there's an extra power of r here. And r is small, because I only need to put this near the boundary. So r is small, so this guy here basically is r to the 1 minus k divided by k times epsilon. So this epsilon, let's absorb on this term. So I get the whole thing is greater than this. It's a different constant. And then on this term, now I just do coefficient watch with epsilon. This guy with epsilon, I also solve on the right hand side, absorbing this term again, and then the estimate one of this. Okay. So the whole thing is that there is this cancellation. See, these terms, they don't have smallness, nor do they have a sign. So they need to cancel. Okay? So they do something to cancel. And they do because this operator just comes with the right structure. Okay? Okay, so that proves the coercivity, and once you have the coercivity, then you can do energy estimates. I'm not going to do that, but now you have your correct energy, right? Then you just go ahead and do energy estimates. Again, for the energy estimates, it's crucial that when you interpolate, you get only one factor of B. You want to get a factor that's linear in B because of your continuation principle. And for that, again, we rely on these very powerful interpolation theorems that Mihail and Daniel have there on the page. Okay. So basically, that tells you how to get energy estimates. And then we have to go ahead and construct solutions. So for that, there's some regularization argument that needs to be done. So maybe I mention this. For this and things. Okay. So in the end, to get solutions, there is a regularization of, first of all, time discretize the problem. Right, to have a time step epsilon, and you want to take the time step to 0 to get the. So there's a regularization. And then there's an iteration. But this iteration has 2 steps. Because now we discretize the problem, remember the boundary is moving. So when you iterate, you cannot only iterate the solution. You have to iterate the boundary. So it is like the transport of the boundary. And then there's the iteration of the solution themselves. And the iteration of the solution themselves is done using an Euler method. Okay? And what's very curious here is the following. If you look at each one of the steps separately, they lose derivatives. Separately, each one of them lose derivatives. But then you combine them together, there's an extra cancellation. And the cancellation that happens here is precisely the analog of that cancellation that I showed before for the linearized equation. Remember, the linearized equation, the big idea is that the linearized equation has a special cancellation which comes from the linearized material derivative. And in a different form, that same cancellation appears when you look at these 3 steps combined together. Separately, they lose derivatives. When you combine them, there's an extra cancellation. Now, of course, if I discretize the problem and I take the limit, the sort of continuum limit, for that I need to control iterations. Now I want to control iterations with my energy estimates, but my energy estimates involving ddt, right? And what do I mean by ddt if now my time is discrete? So what I have to do in the end, what I do is like every time that you have a dt, you can replace by a regular d by using the equations. So you can sort of recast all the energy estimates as estimates for operators defined at a fixed time if you simply reiterate the dt material derivatives in terms of spatial derivatives. And then the energy estimates can be translated to estimates for the discretized problem, and that's what allows you to control the solution to pass to the limit. And that's how you get solutions. Okay? So that's for existence. Then there's uniqueness. It's a whole different story because uniqueness you want to compare to solutions. But then again, you 2 solutions are defined in different domains. Okay. So to do that, we construct some functional that's able to compare solutions in different domains, in part by measuring it on the boundary. And you show that this functional is propagated by the flow. So that part is kind of technical, relies a lot of boundary layer ideas. And for that, again, we relied on this other work that Daniel and Mihaela have, where they have studied the classical problem, and they have a similar approach for the classical problem, where they do uniqueness using comparing things in different domains. Okay, and then finally, there is a continuation of the data, and if you want to show continuation of the data, you always have to do something like a regularization, right? That's the same regularization we use for solutions. Okay? And that's how then everything comes together. Okay, I'm going to be owing to you to talk about fluid viscosity. I didn't have time to get there. That was the other talk for over. Clearly, I was too ambitious. But the topic of relativistic fluids with viscosity is going to be the topic of my talk tomorrow at the BHI conference. So that's why I'm not so worried that I didn't cover, because I'm going to cover tomorrow. So come and hear about fluids with viscosity tomorrow at the conference. Okay, so that's it.
So, any questions on Zoom? I guess I had a broad question.
Yeah.
Could you talk a little bit more about this comparison of domains?
Yeah. So you have like two domains. They start together. They don't have to stay together. So what you can do, you can take the intersection of these two domains, and then in this common region, for both solutions defined there. So then you can do like a kind of inner type of estimate for the difference, right? But then you have to somehow get an estimate for this. And so here's like this kind of boundary layer that I refer to earlier, because you have to sort of balance the solution, but also with the size of this difference of the domains, right? And that's what I'm saying by you're getting something by sort of measuring the distance between the boundaries, because somehow you have to say how large or how small this distance of the common domain is. And an estimate for this basically is telling you how apart these two boundaries are. Okay. Now, so here you kind of do kind of energy estimates, and then here you do sort of kind of boundary layer type of estimates to compare these two things. And then when you combine the three things together, you can get a sort of an estimate that tells you that a suitably constructed vector field, which is not exactly material derivative, sort of because now you have two material derivatives, right? You have the dt for one solution and dt for another solution. So you construct a sort of average of these two guys, and for that average, there is a functional that measures these things that's propagated. So we can bound in terms of initial data, right? And then that tells you to know if the data is equal times 0, then it's going to be equal to later time. And the function that's propagated is very much inspired on the linearized equation. Right? So the function that's propagated is going to be something that is of the form 1 minus k, where these are tilde some suitable average of the r's of the two domains. And then you have something like r1 minus r2 plus r square v1 minus v square, integrating the common domain. Now this is very much like the energy that I showed you before. There are two energies, right? Just like r to this power, r squared, s squared and w squared. Okay, so this is again referring to this philosophy that the linearized equation plays a central role. Even when it comes to this business of doing uniqueness and comparing the solution to different domains and so on, you're still getting something that's kind of coming from the linearized equation. Now, I should mention that, there's a way you can avoid all this. And then mention that, which in fact is the approach that's commonly used, which is the following. If you have this moving domain, let's look at one domain. Of course, you can always straighten domain, construct a map that maps everything to a fixed domain, right? But of course, this map depends on the solution. So when you do that, then you can write the equation in the fixed domain, so that's an advantage, but you introduce new non-linearities in the problem. And the non-linearities that you introduce are bad. Okay, so this just looks like a solution, because you can fix the domain, but of course, you're not going to get rid of the moving domain just by changing of values, right? So that's still going to be present somehow. It's present in the fact that the mapping depends on the solution, introduce some non-linearities in the problem. Okay, so when you write the equation in a fixed domain using this, in the fluid dynamics jargon, you say that you're writing the equations in Lagrangian quantities. And when you write in the moving domain, you say that you're writing the equations in Eulerian quantities. That's with some of the fluid dynamics jargon.
And the continuous dependence is the
So the continuous dependence.
same.
Yeah. So first, again, you have to now you are again looking at solutions that have different domains. So you have to define a topology that's space H2L that I define for you. So you have to define a topology on that, talk about dependence. But in the end, it's like, even for doing for fixed domain equations, if you want to show continuous dependence domain, you need some regularization, right? Because so if you have a solution, HS for data in HS, and you want to show continuous dependence, what do you have to do? You have to look at the difference. U minus U naught, and you need to get an estimate for this guy, right? But once you plug this in the equation, that's going to create a source term that's going to lose derivatives, right? So for if you're looking at if you're doing this for a wave equation, for example, right? And let's say that you're doing for 0, right? So if you're going to get an estimate for the difference, the data appears as source term, and of course, if the data is in AGS, you're going to get a continuous dependence in AGS, this guy is going to be in AGS minus 2, you're losing derivatives. So that's why typically if you want to do continuous dependence, you have to do something like a regularization, right? That's what we do. We have a regularization, but regularization is more complicated space that things are moving, right? Another approach you can do for continuous dependence, you can use like this abstract framework of Kato. There is this classical paper like the Cauchy problem for quasi-linear, what is that? Cauchy problem for first order symmetric hyperbolic systems. It's a classical paper on ARMA. And where he writes everything as this abstract evolution equations in finite spaces, right? And that also allows you to get continuous dependence, and you don't need to do regularization. But I have no idea how to apply that framework in this sense, right?
There's a question in the chat from Brian Lutzak, which says, "Thank you, Marcelo. Could you say a bit more about transporting the boundary with time step? Would this be done in Lagrangian coordinates?"
No, we're doing Euler. For in Lagrange, you don't have transport because the boundary is fixed, right? Yeah, it's like so. So you're really saying that your point on the boundary at the next step is going to be your point on the boundary in the previous step plus like what? Plus like epsilon. Yes, plus the velocity, right? Times epsilon, right? Yeah, because the velocity is like the difference of x divided by time, right? So xi plus 1 minus xi divided by epsilon, which is the time, that's the velocity, right? So if you do like an Euler iteration for the point on the boundary, you just iterate the boundary like this. Does that answer your question?
Thanks, yeah.
Okay, so I think we're we're right on time.
Any other questions? Okay, if not, let's thank Marcelo for bringing Minicourse.